going to deal the nodal method of analysis. As a recap, we have gone through the definition of circuit elements, network topology, circuit laws, which includes the KCL, KVL and Ohm's law, and the equivalence of circuit elements and star delta transformation. Now the question arises when we are able to solve the question using the KCL, KVL and Ohm's law, what is the need of special methods of analysis? So look to this particular simple diagram which is having three resistances R1, R2 and R3. As per the Ohm's law, we are assigning the unknown currents I1, I2 and I3. We are correspondingly associating V1, V2, V3 in terms of the currents and the resistances. So these particular is going to have three relations. Then to solve, we are having say a KCL relationship at this particular junction A, which is suggesting I1 is equal to I2 plus I3. We are also having two KVL relations. One is pertaining to, let's say, this particular closed path, so which is V is equal to V1 plus V3. Another you can frame V2 is equal to V3 because they are connected in parallel, or you can have the KVL relation V is equal to V1 plus V2. So ultimately we are having say the 6 such relationship for 3 element problems. So 6 unknown I1, I2, I3, V1, V2, V3 likewise, and 6 relations. So ultimately the number of unknown variables, number of equations are needed to be solved, which are coming out to be twice the number of circuit elements. So special methods are directed to reduce this computational efforts. So the purpose of the analytical methods is to minimize the computational efforts. They has to have a focused approach, and importantly that can be implemented on computers. So computer realizability is also an important aspect likewise. So with this background, we will be having two methods of analysis, mass method of analysis and the nodal method of analysis. In this lecture, we will be discussing the nodal method of analysis. Now this nodal method of analysis is an application of Kirchhoff's current law. Now the point here, how we are able to reduce the number of variables. So instead of having say branch current or branch voltage, it deals with the node voltage as variables. So this is a significant departure from the KCL, KVL approach. Now when a circuit is having n nodes, we will be requiring maximum n minus 1 nodal equations. So this particular maximum is important, and this will be clear while say we will be discussing the various examples likewise. Now the procedure is identify the nodes and select one of the node as a reference one. When say there are say n nodes, we have to mark one of the node as a reference one, and with respect to that reference we will be expressing the voltages of other nodes as nodal variables. Assign the voltages to remaining nodes as V1, V2 up to V minus N1. These voltages are referred to with respect to reference node. Now we have to write the KCL equation for each of these n minus 1 nodes while considering the branch currents in terms of the node voltages. So please remember that we are now expressing the branch currents in terms of the node voltages. Now to minimize the mistakes and to write the equation in one of the standard form, it is requested that you keep the outward current as positive. So outward current has to be marked positive, otherwise it is a general method. So you can say the inward currents can also be marked as positive. So out of the two nomenclature we have to follow one, and here the outward currents are marked positive. So this particular is having say the approach where the mistakes are expected to be less. Now we, after writing these particular n minus 1 equations, we will be rearranging these n minus 1 simultaneous equations and then solving to find out the unknown node voltages. After having say the unknown node voltages known, we can calculate the branch currents or voltages as and when needed likewise. So just to give you the fundamental aspects, This particular is having say 3 nodes, 1, 2 and third one. So one of the node has to be marked as a reference. So these are, you can say, the various symbols which are used for marking a reference node. So normally we are saying the reference is a datum node, so it is coinciding with the geometry, and this particular is a bottom node is marked as a reference one. Otherwise any of the node can be marked as reference. Now the point which we have to remember, why we are insisting that the outward current be marked positive. So you keep in mind that the Ohm's law dictates that the current flows from higher potential to the lower potential. So this particular is the arrangement of a voltage across resistor. So the current to which terminal to which the current is entering is marked positive likewise, so that is having a higher potential compared to the other terminal. Now that particular is there. So you have simply given say the two nodes V1 and V2 are marked there. Now we are, let's say, writing the equation for this. Correspondingly we have to mark the outward current as positive. So in this, that these red arrows are coming out to be the temporary arrows which are not the permanent one as such. So corresponding to this, at this junction this is a outward current, this is outward current, outward current and outward current. So how we will be able to write the outward current equation for this? V1 upon R1. Corresponding to this one, we are presuming that this is a direction. So V1 is at higher potential with respect to V2. So that particular is giving you the value V1 minus V2 upon R3. This particular IA, which is a actual current source, which is opposite to the our convention of the outward current. So that particular is with minus IA. Here say it is IB which is coming out to be positive. So this is how say the nodal equation is there. Although say we are writing the equation as an application of KCL, but only say the node voltages are participating as unknown variables. IA, IB, they are the current sources, so they are known in advance. Now when say you are writing the nodal equation for node 2, you have to presume this is at higher potential than this one. So the reference direction of the outward will be like with say the blue arrows. So correspondingly the equation will be V2 upon R2. Here say plus V2 minus V1 upon R3. So this particular is of interest because that is corresponding to the common element. Similarly this particular is also of IB of source, so that is of different color. Now you please be mindful here. Here say V1 minus V2 upon R3. Here say in the other equation V2 minus V1 upon R3. So depending on the actual numerical value, the current will be flowing in one direction, other will automatically be taken as opposite to that. So there should not be any confusion. Here say the current is outward, so it is coming out to be with positive sign. In case of second, the IB is coming out as inward, which is opposite to the reference of the outward current, so that is participating with the negative sign. So I believe that there should not be any confusion in writing the equation at node. Now there are say the different cases. It can be with the only current sources and where say the voltage sources are present. Now please be mindful that the nodal analysis is an application of the KCL, so it is dealing primarily with the currents. So that's why we are first considering the presence of current source, then it will be made as a general arrangement where say the voltage sources are also connected. So this particular is again say the reference circuit. Here say we can easily identify the nodes. This particular is one node, another node, another node, another node. So there are say 4 nodes in this particular. These particular are marked. Now one of the node has to be marked as reference. So this particular is marked with the 0, so that is to be taken as reference. We will also be assigning the voltages V1, V2 and V3 corresponding to the node 1, 2 and 3. Please be mindful that these voltages are or will be with respect to the reference. So the situation will look like this. Now for this we have to write the nodal equations. So nodal equations are to be written for node 1 with a variable V1, node 2, node 3 likewise. So we will be developing the equations in one by one manner likewise. Now corresponding to V1 you are simply following the outward current as positive terminology nomenclature. So here say the current in this V1 minus V2 upon R1. So that particular is constituting the first term. V1 minus V3 upon R4, so that is the second term. Here say the current is injected into the node, so that particular is participating with the negative sign. This procedure has to be repeated for the second node, so that is giving you the V2 minus V1 upon R1 plus V2 upon R3 plus V2 minus V3 upon R2 likewise. On the similar line you have developed the equation for the third node as well. Now the next step is we have to rearrange these particular equations, and that equations are rearranged into the matrix form. So this matrix form is also giving you some idea how we can write the equations as such in general, but the question is they are rearranged. So here say V1 into 1 upon R1 plus 1 upon R4, so that particular is one element. Similarly you have marked the other element of this matrix. Now the question is, when say we are able to write the equation into the matrix form, we can solve it using any of the general methods like say the Cramer rule or matrix inversion. So that particular is giving you the arrangement. The same diagram is represented here. The same equation which has been discussed previously is taken here as it is. Now just to give you a general nomenclature, this is coming out to be a 3 by 3 matrix, so it is also referred as 3 by 3 matrix. The reciprocal of the resistance is the conductance, so the G nomenclature is used as a matrix terminology, which is a double script nomenclature to give you the row and column. So the components are marked G11, G12, G13 likewise. So if you are making a comparison, you please have a careful look. G11, it is the sum of the conductances connected to the first node. So first node is this much, so R1 is connected, conductance will be 1 upon R1, R4 is connected, so the corresponding conductance will be 1 upon R4. The summation of the conductance will be like this. Where say G12, it is the mutual term which is negative of the conductance between the node 1 and node 2. So negative of the conductance between node 1 and 2 likewise. So basically you can write this particular equation directly into the matrix form by inspection. So the same process has to be repeated and so on. So when say we are able to standardize the term Gij, I and J are different, so that particular is suggesting the mutual term which is the negative of the conductance between the ith and the jth node. Similarly Gii, which is a self term, it is sum of the conductance between, or you can say sum of the conductance connected to the ith node. Vj, it is the jth node voltage with respect to the reference, and lastly the Ij, as per this nomenclature, it is the injected current into the node. It is the current which is injected into the node. So you please follow, into means it is there, so basically the on the right hand side it is participating, and that's why it is positive sign. IA. Second one, there is no current source present, so 0. Third one, it is having a injected current IV, so I3 will be equal to IV. Likewise, once that particular is there, we can solve it by the Cramer's rule, or you can have a matrix inversion techniques likewise. Now take one of the example on the basis of the same. So the same equations we have referred as a procedure. You are in the beginning, you are requested to follow the equation by equation steps. Try to summarize this particular equation by inspection. Try to validate the results from this particular, the way you are done by eliminating the variables. Find out the value of unknown voltage V1, V2, V3, and here say by the matrix inverse techniques or by the Cramer's rule. So these are the equations. Same thing, V1 minus V2 upon 2, V1 minus V3 upon 4. So simply the numerical values are substituted. Correspondingly, we will be getting the results 27.43 volt, 20 volt, 30.28 volt. Take another example. Here say the current source is there, which is between the two non-reference nodes. So there is no special consideration. You have to write the KCL equation for node 1. What is this? V1 minus V2 upon 2 plus V1 minus V3 upon 4 minus 10. So that is first. Second equation, V2 upon 4 plus V2 minus V1 upon 2. This is also the outward current, so plus 4 ampere is equal to 0. For third, this 4 will be the inward current, so V3 minus V1 upon 4 plus V3 by 8, then it will be inward current, so minus 4. You have rearranged this particular, so these are basically participating on the right hand side. Equation is coming out to be like this. You can validate this simply by inspection. So corresponding to G11 1 by 2 plus 1 by 4, G12 minus of 1 by 2, G22 which is the sum 1 by 2 plus 1 by 4. There is no conductance present between 2 and 3, so that particular is 0, and this way you can sum up the equations likewise. The solution is obtained as this. Now we are now extending it to a terminology where say the dependent current sources are present. So you can say one of the source is replaced by a current source. So here say the equations are to be developed on the similar line, no special care as such. You are simply treating this as a source. So the equation is coming out to be like this. Now there will be a further relation which will be suggesting the dependency of this current Ix on say other circuit parameters. So in this particular case Ix is indicated like this, it will be V1 minus V2 by 2. So that further relationship is needed. Now this particular Ix, which is equal to V1 minus V2 by 2, has to be substituted in third equation likewise, and then we will be rearranging it. Now the point which is to be noted here, that the G matrix which earlier happens to be symmetric is not a symmetric one here. So this particular symmetry is lost because of this particular current source. And second particular point, we cannot simply write this matrix form by inspection, because we have to manipulate depending on the dependent source, depending on the controlling variable and the controlled variables. So you are encouraged for such questions to write the equation first in the systematic approach, then go for compiling or summarizing them into the matrix form and go for the solution as such. Now we have covered the cases, 3 cases. Now it is a time of summary. So it is an application of KCL. Now one is a polite request that we have to be consistent in writing the nodal equations. Again, as a reminder, treat outward current from the node as positive and inward current to the node as negative. This particular is again is consistent with the Ohm's law, where it suggests that the current flows from higher potential to the lower potential. While writing nodal equation at the ith node, assume the Vi higher than other connected nodes. So in that way, the outward current nomenclature will be taken care of. So this particular is a temporary one. However, say when you are writing for the Vj node Vj, you have to reverse this. So that Vj has to be treated as higher than the other one. Nodal equations can be written by inspection only if the circuit is not consisting any dependent source. So that particular is important. If suppose the dependent source is there, then we have to write the equation one by one and then do the manipulation. Next, we will be discussing the nodal analysis for circuit having the voltage sources as well. So thank you for kind attention. You can go for these books for further reading. Thank you.